Hi, welcome back. In the second part, we're going to talk about some of the elements of a QoS solution that enable reliable delivery of multiple services in a next-generation network. We're talking about delivering reliable packet-based services. Now, packet networks allocate resources dynamically. This sharing of resources means that the packet-based networks are very flexible, very efficient, but also potentially unreliable. So, to make packet-based services reliable, we can think of as giving the right resources to the right amount of the right packets. So let me say what the components of the solution are that do that. So the right amount is to do with the amount of packets to which we're trying to give a good quality of service. Because network resources are limited, we cannot give a good quality to an arbitrary quantity of packets. So at some point there has to be some function in the network which says no more of those. No more of that kind of service can be delivered at the moment. So we call it admission control. Another important function is to be able to distinguish packets belonging to different streams and different services. So we call this packet classification. Some people talk about QoS and the thing that they're really doing is packet classification. And this is a very important function. But it's not enough, because having distinguished packets of one stream from another, we then have to treat them differently if we're actually going to achieve anything in terms of delivering quality of service. And that's done with a packet queuing and scheduling mechanism. So we have to decide effectively which packets we may have to lose when there's too many, and in which order we're going to send the ones we're going to send. Packet queuing and scheduling is where we have unique and patented capability, and we call this GoS, and I'm going to say a bit more about it in the rest of this talk. Before I go on, I'll say something about standards. There's a misapprehension that standards actually have already solved a lot of these problems. We need to be very careful about standards. Standards typically specify models of how they want networks to behave or what should happen, and they also specify protocols. These are means of transmitting information from one place in the network to another. What they implicitly rely on but don't tend to specify is scheduling mechanisms that actually implement the required behavior. So packet queuing and scheduling remains really outside the domain of standards. That's where we can deliver a benefit with our unique IP. So I'll say a little bit more about this now. Packet queuing and scheduling, or traffic management as it's sometimes called, has been studied for nearly 30 years now. It's quite well researched, but it's still regarded as quite a hard problem. And a lot of the older mechanisms, which are still in use today, were not really designed with more than one type of service in mind, because they come from the world before networks converged, when each network was optimized for a particular purpose. So, as an example, I'll use a technique called weighted fair queuing, which is widely deployed in the industry and quite well understood. So in weighted fair queuing, classification mechanism divides the arriving packets into a series of classes. So this is also sometimes called class-based weighted fair queuing. And packets in each class are put into a queue, and within each queue, packets are simply served in the order that they arrive. Where the weighted part comes in is that the way the scheduler decides which queue it's going to take packets out of is dependent on the weights which are given to them. So a queue which is given a higher weight has a packet taken out of it and transmitted more often. The advantage of this is that each class of traffic has a minimum amount of bandwidth that's guaranteed to it, determined by its weight. And we have some isolation and protection of the streams of packets in each class from those in other classes. The disadvantages are that there's no protection within a class, so those packets which get put together in the same queue are very vulnerable to other streams which are going in the same class. So where we have one stream that might be particularly aggressive or very bursty, that will have an impact, an adverse impact on all the other streams which are going into the same class. But most important for the world where we're trying to use packet-based networks to deliver real-time services such as voice over IP and video, this mechanism really provides no means of controlling delay. So because packets just get stuck together all in one queue and there's no means for specifically limiting the length of that queue, packets sitting at the end of the queue will have to wait a long time for the queue to empty, and so the delays can be very high. So our alternative to this we call GoS. We went back to first principles rather than trying to tweak or adjust or adapt or enhance existing mechanisms. We actually analysed the whole problem of queuing and scheduling packets mathematically. And we used the insights that came from that to develop a new mechanism, a queuing and scheduling mechanism that was designed to actually support multiple real-time services, one that provides independent control over loss and delay. And we call it guarantee of service, abbreviated GoS, because rather than just trying to try hard or somehow improve quality of service, it actually guarantees the behavior of streams of packets that are going through the mechanism. So the unique features of GoS are that it provides support for multiple real-time, near real-time and critical data traffic types simultaneously. It's very easy to configure because having a mathematical basis means that the low-level parameters which are required can all be derived automatically from a high-level description. And most importantly for the delivery of reliable services is its performance is predictable. So each class of traffic gets a consistent treatment regardless of the amount of traffic in other classes. Also extremely important is that it's efficient. Other mechanisms which are not really designed to control loss and delay require capacity to be reserved or set aside to cope with occasional, unusual, difficult events. GoS doesn't do that. GoS is designed to deal with those kind of circumstances day one. So there's no need to reserve capacity and no capacity has to be wasted. 90% of the link can be used for traffic that has guaranteed quality of service. And the way that it functions is very simple. So that means it's interoperable with standards such as diffserv and other functions which are essential in a modern network, such as firewalls and network address translation.